Well, hello and welcome YouTube. Mr. Robinson back with you with another brand new exciting video, all math-based of course, and today's focus is going to be on solving equations. What kinds of equations? Just basic algebraic equations, 2 steps, get some subtraction, a little bit of division here and there, maybe some double check. I got 11 problems. Got 11 problems for us to do. Most of them are solving. A couple where you justify the steps as you go, or they give you steps and you justify them, and then some error correction. And that's it. Just transitioning to a few of those. Let's take a look. Now I'm only going to do the problems that are circled on here, not the ones that aren't, so take that as you will. It's fine. I'm going to start with number 3. 4a plus 3 equals 11. Now to make sense of this, what we're doing is we are seeing what value of a would make the statement true. And of course, I'll double check a few of them with you as we do them. Maybe the first one if there's a fraction, see what it looks like. 4 times some number plus 3 equals 11. What is it? Well, plus 3 is occurring last in this. I'm adding 3 to a number and I get 11. So if I subtract 3 from 11, then I'll figure out what that number was before I added 3. So if I subtract 3 from 11, I get 8. Now the reason I subtract 3 over here as well is for balance in the equation. If I'm going to make this side of an equation 3 less, then this side of the equation also needs to be 3 less. 3 minus 3 becomes 0 right here, and all you're left with on this side of the equation is just this 4a. 4a equals 8, or better yet, just saying 4 times a equals 8. 4 times a number is 8. I'm sure you know the numbers too, but if you're not sure, you always divide that number by 4 to figure out what it is, and because this one becomes 4 times less, then so does this side. Now 4 divided by 4 is 1, but as I do this canceling mark, what I'm really saying is that 1a and a are the same thing. I don't need to write 1a, I'm just going to write a right there, and we're good. So a happens to equal 2. 8 divided by 4 is 2. 2 is the value that makes the statement true. A equals 2 is the solution to this equation. To double check it, to check this solution here, let's substitute 2 back into the original equation. 4 times 2 plus 3 equals 11. Let's see if that works. 4 times 2 is 8, and 8 plus 3 indeed equals 11. So 11 equals 11, all checks out, I'm set to go. That's my double check for that. That's just to ensure that that solution actually works. Now this happens to be the only solution that works, and I think we're only looking at single solution equations here. The only other possibility is an infinite number of solutions, which I'll save for later, and no solution cases, which again I'll save for later. We'll see if we get some fraction answers though here in a bit. Number 4. 8 equals 3r minus 1. If I take a number and triple it and subtract 1, I get 8. If I subtract 1 from a number to get 8, then that number must have been 9. How do I know that? Because if I add 1 to 8, I get 9. Now if I add 1 to one side, I also have to make this side larger as well. Negative 1 plus 1 is 0, so that's gone. All that's left on this side of the equation is 3r. 3 times a number is 9. To figure out what that number was that I multiplied by 3 to get 9, you divide 9 by 3 to figure that out. And 9 divided by 3 is 3. 3 divided by 3 is 1, and 1r leaves me with what I'm looking for. 3 equals r, or r equals 3. That is the solution to that one. So you can see what's happening here with both of these sets of equations as we've run into them. On this first one here, 3 was added, so I subtracted. Subtraction is the inverse of addition. Likewise, on this problem, when 1 was subtracted, I added 1 right here. That is the inverse. Addition is the inverse of subtraction, vice versa. Now, both of these had multiplication going, 3 times r and 4 times a. If some number times 4 and some number times 3 gives you those values, then we divide by 4 and by 3 to figure out what those values were. Division is the inverse of multiplication. So you can bet if we get a problem that involves multiplication, division, I'm going to multiply that instead to get that value. Okay, number 5. 42 equals negative 2d plus 6. Kind of same concept here, but now that d is negative, we'll make sure to take care of that as it jumps into play. But I add 6 to a number and I get 42, so let's subtract 6 from 42 to figure out what that number was. And of course, to maintain balance, 6 gets subtracted from that side. I'm not going to say that every time. I'm just giving you the idea. If you're running into this because you have trouble with the problems, I'm giving you the talk as to why it makes sense that we're doing this. My goal really, yes, is to isolate this variable. I understand that. But if you talk about it logically and as if you haven't been taught the algebra before, just think of it like going backwards. I add 6 in the end to get 42. So what number did I add from 6 to get 42? Do 42 minus 6 to figure it out. The only thing here is the balance. If I subtract 6 from one side, I can't make one side 6 less than the other side. I have to make sure that I keep both the same size. So 36 on one side, negative 2d on the other side. I take d and I multiply it by negative 2 and I get positive 36. The only way that you get a positive product from one negative factor is if the other factor is also negative. Remember, stand and deliver. A negative times a negative equals a positive. Say it. You remember that one, right? So we say that all the time. Now, so we expect a negative answer. So how do we get that answer? Something times negative 2 gives me 36. Let's divide by negative 2 to figure out what that thing is. Now remember, it's a negative 2. Keep in mind that right here, see, some people, if you think you know the algebra, you might accidentally divide by 2. And you're like, okay, these are both 2, so they cancel. Well, be very careful about saying that, because negative 2 divided by 2 is not positive 1. We need that to be a positive 1 here, so we need to divide by negative 2. Negative 2 divided by negative 2 gives me positive 1, and that's my result. A positive divided by a negative gives me a negative. So this is negative 18, and that is what my 1d represents there. If I wanted to double check it, I would get negative 18 times negative 2 is positive 36, plus 6 equals 42. That pans out. I'm skipping number 6. Maybe it was because it was a decimal. I don't know. I had to chop away some problems, so that's one of them. Let's look at 7, 8, and 9 here. Number 7, 15y plus 31 equals 61. Okay, the numbers are getting bigger, but that doesn't mean they don't necessarily get smaller here. Like, take a look. If you've gotten used to the familiarity here, I don't know why I wrote 30. You subtract 31 from this side of the equation because we're going to subtract 31 from this side. What you're going to start seeing is, you know how subtracting 31 from this side to start? I'm going to really start doing it on this side more so and say if 31 is on this side and if it's affecting my variable, if I'm trying to get my variable by itself, my end goal really is simply just to move the other terms on the other side of the equation. Move everything that's here over there, and by moving it, I mean getting rid of it on one side, 31 minus 31 is 0, and having it left for me on the other side after I've subtracted 31 from that side too. So that's kind of how you're going to hear me talk about it for the most part. 15y is all that's left on this side, and 61 minus 31 gives me 30. 15 times a number is 30. Because 15 is multiplying by this number, I'm going to divide both sides by 15 right here. And again, for balance purposes, 15 over 15 is 1. And then you're left with 30 divided by 15, which is 2. So y equals 2. So again, the whole goal for all these problems is you're kind of making sense. If this is your first time seeing them, or you were struggling with them and you're not sure, these are called two-step equations, and it takes 2 steps to do. My first step generally involves some constant that's on my expression with my variable, and I need to move it over to the other side by addition or by subtraction. Based on whichever one was given, you do the inverse, you do the other one. And then the next thing that you tend to see here, it looks like that there's a coefficient, a number that's in front of my variable that I generally need to divide because it's multiplying by that variable. So I divide by it to get my variable by itself. I want to know what x is, then I just want to know what x is. I don't want to know what 2x plus 9 is. I don't want to know what 2x is. I want to know what x is. A single x, what that represents that I could plug in. And that's what we're looking for when they ask us to solve. That is our solution for our unknown variable. We know everything else, but we want to know what value for the variable makes this equation work. So that's the goal. So let's jump into number 8. This one, it doesn't get trickier, but it is new looking. Because there is no coefficient that's written in front of here. So let's see what you can do with it. 9 minus c equals negative 13. The goal is to solve for c. You could say I take a number and I take 9 and I subtract a number and I get 13, negative 13. What's that number? There's a little fly in the ointment there because I don't want to think of the number that I get to subtract to get negative 13. So let's just go with the algebra. Let's go ahead and I want to get this variable by itself. I want to get c positive c all by itself. So I'm going to start by subtracting 9 from both sides. This 9 is on this side of the equation and it's bothering me. It's bothering you too, I hope. Subtract 9 from both sides here. Notice it was a positive 9, so I subtract. 9 minus 9 is 0. Make sure you know what's still left on this side. It is a negative c, not just c. there's a negative c right here, a c that's being subtracted, if you will. Negative 13 minus 9. I have a whole video dedicated to this. It's like 13 plus 9, but the answer is negative. So this is negative 22. Okay. Two ways you can look at this. One kind of more logic step. Let's just talk about that first. Negative c equals negative 22, or the opposite of c is negative 22. If the opposite of c is negative 22, then regular c must be positive 22. So that's the logical way of getting that. We're not done right here. You have c kind of by itself, but there's still a negative in front. And that's the idea. Notice how every time I mention that these things cancel, I don't really want to say cancel, 15 over 15 becomes 1. If I wanted to, I could have written 1y equals 2, and that would have been fine. You're not going to see an answer key that says that. Teachers won't lend to that. It is implied. Just like, remember where this was 31 minus 31 is 0? You didn't see me writing plus 0 here because I want to make this look cleaner when I can. I want to give myself the impression that that is non-impacting, that if I don't write it, nothing's going to change anything. So by canceling, it means I don't write it anymore. But by stating that it doesn't exist is kind of the wrong way to put it. So this is 1y. A single multiple of y gives me 2, whereas 15 multiples of y gives me 30. And then plus 31 is 61. But right here, I need to know what one multiple of c is. One positive multiple, not a negative one. But that being said, the coefficient that's in front of here, although not written, is indeed a negative 1. Negative 1 times c gives me negative 22. And why is that important? Because now, in case you're not sure what you could have divided by, if negative 1 is multiplying by c, I can divide both sides by negative 1 right here. And negative 1 divided by negative 1 gives me positive 1. So positive 1 right here is cancel. It gives me a positive 1c equals 22, and that's what I'm looking for. So that's where negative divided by negative gives me a positive right here. 22 divided by 1 is 22. That gives me my final result on that one there. C equals 22. Okay? Cool. Number 9. X divided by 6 plus 4 equals 15. Okay, we're dealing with a fraction here. There are multiple ways you can do this problem. I'm just going to go kind of with the way we have been doing them. I'm going to stick with that principle of get x by itself by doing inverse operations. That's fine. Check this out. I'm going to try and do this mentally with you, though, this very first step. What's the first step? If 4 is being added at the end to get 15, I subtract 4 from both sides, right? Can you, on your own, without writing minus 4, and I'm only stating it because I know future problems in a bit won't have the steps, can you do it without actually writing the minus 4s and actually comprehend it okay? If I subtract 4 from this side, it's gone, right? It's gone. All that's left is x divided by 6. If I subtract 4 from this side, 15 minus 4 is 11, so all I have left is 11. So I went from one step to the other without writing minus 4, and when I do it in my classes, I'm going to start getting to that at some point. People might ask, wait, well, how'd you get to that step? And I'm going to, it's implied. I subtracted 4 from both sides, so there's that. Okay, I take a number and I divide it by 6 to get 11. Now think of that logic step. I divide a number by 6 to get 11. 66. I know you know the answer. It's okay, Carl. But to figure out this actual answer in good math terms, what number divided by 6 gives you 11? Do 11 times 6 to figure it out. And the reason why I'm stating that is because I want you to get used to this syntax here. If I multiply 11 by 6, I'll get my answer. Keep it balanced. I don't just multiply one side by 6, I do the other as well. Times 6 times 6. And we mentioned how these things cancel out. Well, they do. They cancel because here I divided by 6 and here I multiply by 6. This actually right here is 6 divided by 6, which is 1. It might not look like a fraction right now, but the thing with fractions and multiplying is they can join together. Case in point, I can write a divided by b, a divided by b times c divided by d, and that actually happens to equal a times c divided by b times d. Whether it looks like this a is dividing by d or not, because it's multiplication, it actually is. A is dividing by d just as much as c is. You don't have to write it over it. You don't have to even write it within the same fraction, but they are there. And this 6 is really 6 over 1. It's in the numerator, 1 is in the denominator, x divided by 1 is x. Whatever. Point is, x equals 11 times 6. 66. Carl knew the answer. I know that Carl knew the answer. But it's really about approach. What does this problem perceive to do so you don't mess up? Scrolling down, skipping some of these, getting to number 13, another fraction problem. Let's see what we can do with this one as well. Same kind of idea. The 4 is a constant term in this expression that's kind of bothering my m. I need to get one m by itself. So let's subtract 4 from both sides. Let's try it again without writing anything. Minus 4 minus 4. This 4 is gone. Notice there's still a negative. Negative m over 2 equals 10 minus 4. That's 6. Now there's a negative here, and notice this negative's kind of in the middle, and I didn't really draw it well in the middle, but I'm going to. It just means that my whole value is negative, and I do need a positive one in the end, so probably think of it more like I need to multiply by a negative value to get this done. Think of it probably more so as this. I'm really taking m and I'm dividing it by negative 2. You can move this negative down or up or keep it in the middle. There's only one negative that's applying in this whole fraction. I'm going to apply it to the one that makes most sense for me to find my inverse. If I'm dividing by negative 2 with my m, if I'm taking something and dividing by negative 2 to get 6, I'm going to multiply by negative 2 to figure out what my value is. So multiply both sides here by negative 2. 6 divided by negative 2 gives me negative 12. And the negative 2's cancel. I probably wasn't actually going to write these, but I did. And I'm left with m on this side, which is great. I get my final solution, m equals negative 12. Let's go and double check one of those before we get to one of these ones here. So if I substitute negative 12 in for m, what happens? I get 4 minus, notice this minus right here. I'm going to substitute in negative 12 for m, divided by 2, and this equals 10. 4 minus negative 12 divided by 2 is negative 6. So I'm subtracting negative 6. If you saw the video before, subtracting a negative is equivalent to adding. 4 plus 6 equals 10. So 10 equals 10. That seems to check out. All right. All right, so those are some solving equations problems. Hopefully those are making sense so far. I have 4 more problems to do. The next 3 are just justifying each step. Probably say, how do I say it? I'll say what property of equality it is, and then I'll state what I'll write down what I literally did math-wise or what happened, because they don't show you the steps. Maybe I'll show you a couple of them so you can make sense of them. But 15, 16, and 17 are kind of like writing out why what they did works. So for example, number 15, I'll write some stuff in between and see if it makes sense. 2x minus 5 equals negative 20. If my goal is to get x by itself and solve for this thing, my goal is to isolate x by applying inverse operations to everything else that's happening here. The minus 5 and the times 2 are going to somehow be inverted. So if 5 is being subtracted from both sides right here, why don't we go, or excuse me, 5 is being subtracted right here, why don't we add 5 to both sides right here, and then this is where those 5's cancel, become 0, and all that you're left with is 2x. And negative 20 plus 5, check that out, is negative 15. So what did I do going from this step to the other? I used something called the addition property of equality that states I'm going to add something to one side, and to maintain balance in my equation, I'm going to add the same thing to the other side. I chose 5, not me, but the thing did. We chose 5 so that it completely eliminates the negative 5 on this one side. All that's left is 2x, so I can continue isolating my variable. So it's called the addition property of equality. What did I literally do? I'm going to type it out just because I want to. It's add 5 to both sides. That's kind of big. Maybe I'll just write it out next time. It's kind of annoying. Add 5 to both sides by using the addition property of equality. Okay. Next one. 2x equals negative 15. 2 times the number is negative 15. So we divide by 2 to figure out what it is. We divide both sides by 2. We divide this side by 2 and this side by 2. And 2 divided by 2 is 1, and that leaves me with my 1x right here. Negative 15 divided by 2 is what's left here. They could write it as negative 7.5, but they don't. I love improper fractions myself, even if I can get decimal answers. Depends on the problem. If it was a question of money, I would probably say 750, negative 750. Justify my reasoning. That's the division property of equality. Something was multiplied on this side in order to isolate my variable and maintain balance, I have to divide by 2 on both sides. That's literally what I did. I divided 2 on both sides. Those are good justifications. Now I'm going to stick with those for these other ones. I'm going to do them a lot faster. Now that you're probably making sense in what happens. Number 16, x over 3 minus 7 equals 11. In order to isolate the x over 3 term, this negative 7 must go. And using the inverse of subtraction, which is addition, I must use the addition property of equality. I must add 7 to both sides. Add 7 to the left side, negative 7 plus 7 is 0. Add 7 to the right side, 11 plus 7 is 18. So I add 7 to both sides. That is the addition property of equality, and that's taken care of. X divided by 3 equals 18. Okay? If x divided by 3 equals 18, what was the previous value for x to make this one work? Well, if something divided by 3 is 18, to figure out what the previous number is, let's multiply both sides by 3 to figure it out. X over 3 times 3, the 3's would cancel, and 18 times 3 gives you 54. So x equals, there's a mistake here. I don't know if the book knows that these are supposed to be, there's a mistake in the book. This should say x equals 54. See, they divided by 3. That's wrong. Keep in mind, that says x divided by 3. I'm not doing 18 divided by 3. I'm taking a number divided by 3 to get 18. 54 divided by 3 happens to give you 18. I showed that by doing 18 times 3. I didn't show it yet. I'm probably not going to write it, but that's the idea. Hey, book was wrong. There's actually a question we're going to do later where it's error correction. Maybe this was supposed to be, but there was a mistake. That, or maybe this was supposed to say 3x. I don't know. But let's do the x over 3 because we don't see those enough. X equals 54. I multiplied by 3 from both sides. That's a multiplication property of equality. Multiply 3 on both sides. That leaves me with that 1x. Okay? Number 17, before I do 26 here, 9x over 4 equals negative 9. All right, there's more than one way to do this problem. It depends on order and how many steps you want to do. We're going to keep 2 steps from here. It clearly shows 9x attached at the hip, almost like you want to leave them together. And you see that they do on the next step. They keep the 9x. Where did the divided by 4 go? Well, if you divide something by 4 to get negative 9, then let's multiply by 4 to figure out what that number previously was. Times 4 on this side, times 4 on that side. That's called the multiplication property of equality. We'll multiply 4 on both sides. That cancels the 4 down here. Left with 9x. Negative 9 times 4 is negative 36. 9 times x equals negative 36. Divide both sides by 9. Division property of equality. Divide 9 on both sides. You're left with x equals negative 4. And that one seems to be correct. Notice there was no constant term on this one. Nothing to add or subtract. You only add or subtract if there's a term that is separate from your x term and it's a constant that you want to move over. Again, that's being added or subtracted. Okay. Last problem, number 26. Explain the error. We just had a previous error. Hopefully I explained it, but let's talk about this one. Find the error in the solution and solve correctly. Okay. So here's the original problem. Let's call these next steps, and the step is kind of in between, but the step that you do before to land on this one. So step 1, I'll write in Roman numerals, step 2 and step 3 are what you land on after performing an action. So let's say this is the original problem and step 1 is going from here to here, and step 2 is going from here to here, and step 3 is going from here to here. Just so you can identify where any mistakes might be made. There might be more than one. And keep in mind, if you make a single mistake and never correct it or never somehow reverse back to correction, your answer will be wrong. And that's okay. It's like, say you have a 10-step problem, and on the very first step, there's a 2 plus 2, and on the next step you write 5, like 2 plus 2 equals 5. Obviously, it's wrong, and that means every other step after it's going to be wrong because you went by assuming 2 plus 2 was 5 to do the rest of your math. But that's, like, fine. As long as we identify where the one step was that led to that, we'll go ahead and just address that one. The rest we just assume to be true based on what happened. But when we correct it, you'll notice everything changes. if the step that's wrong is early. I don't know. I haven't done it yet. Find the error in the solution and then solve correctly. All right. Here's the original problem. 9x plus 18 plus 3x equals 1. Say I'm looking at a student's work, and I have to assume to know what they did to go from one step to the next so we can make sense of it. The next step shows 9x plus 18 equals negative 2. Now, a couple things happened here. The 3x is no longer on this side anymore. It didn't combine like terms with the 9x, and we'll talk about combining like terms, but it didn't combine like terms. It's like it's gone. It's like I'm taking it here. Oops, I don't want the circles. It's like I'm taking it here and wiping it off the old face of the earth. But notice, it's not just gone, because I can't just get rid of it. I need to have balance in an equation. Notice how this 1 is no longer a 1 on this next step. When 3x was gone, it turned into a negative 2. So we have to presume, how the heck did the 3x go away here and the 1 turn into a negative 2? Well, you saw as we moved things from one part of the equation to another by subtracting things over if they were added, like this one. If 3x is being added, maybe we subtract it on this side. What if I did minus 3x to both sides right here? 3x minus 3x goes away, and 1 minus 3x is negative 2. 1 minus 3x equals negative 2. I haven't talked to my class yet about combining like terms, and unless they know about combining like terms, notice how every problem that we did beforehand with that x, I never merged it with the other number. If it said 2x plus 7, I didn't turn it into 9 or 9x, because they can't combine. There's a deeper meaning to that I don't want to get into this video. I'll do it in a different one or something. I've done it before. But those don't combine here. So it looks like, although they had good taste, I don't know. They had a good idea brewing to subtract 3x from both sides in some sense to get this x by itself. There's a lot more that's wrong with it, and I'll talk about it. 1 minus 3x, although 1 minus 3 equals negative 2, 1 minus 3x does not equal negative 2. There's an error in step 1 right here. So let's get rid of this minus 3x here. There's an error in step 1. What is the error? There's something that they did that they shouldn't have, to subtract 3x from both sides, and I'll talk about why. But they combined like terms wrong. Combined 1 with negative 3x when you can't. All right. 1 with negative 3 can combine and give you negative 2. Did we have a negative 3 here? So, just think about how that works. Now, here's the other thing. My goal is to solve for x. My goal is to get x by itself. I have two different terms that have x in it, a 9x and a 3x. Even if the person chose to subtract 3x from this side and move it to the other side, it's going to go onto the other side. I'm going to have an x term in the right expression of the equation and an x term in the left expression of the equation, and that's not helping me get toward my goal. When you do solving for a variable, you want to get all your variables on one side of the equation and then combine them all. That's what you want to do. So I'm going to go back to this problem. Well, actually, first let's make sure there are no other errors. Let's take a look at the rest of what they did. I'll talk about combining like terms after. Looks like they subtract 18 from both sides because it's gone from there. Negative 2 minus 18 is negative 20. That's true. And then 9 times a number is negative 20, so divide by 9 to get that last thing, x equals negative 20 over 9. Okay, so the rest of their work was good, but it was based off a poor pretense and kind of an ill-advised first step. So we're not going to do that. That's the wrong answer because of what they did before. So let's address this. 9x plus 18 plus 3x equals 1. So I talked about combining like terms. I don't want to subtract 3x over. Instead, I want to simplify this left expression right here. I'm going to first start with the commutative property of addition. I can reorder these things. I'm going to put the 3x next to the 9x in this addition just to make easier sense of what's happening. The 18 switching with the 3x, that's fine. I didn't change anything. Now to simplify, 9 multiples of x, x plus x plus x plus x plus x, 9 times, plus 3 more x's, x plus x plus x, is 12 total x's. 9x plus 3x equals 12x. Just like 9 plus 3 equals 12, these two can combine, the 9x and the 3x. That's actually allowed. 12x plus 18 equals 1. Notice I didn't do anything yet with the 18. I'll do it in a bit. But these two combined by addition. That's allowed. 12 multiples of x. Okay, this is just like any other equation that we had. Let's get x by itself. 12x plus 18 equals 1. Let's subtract 18 from both sides, just like they did here. Let's subtract 18 from both sides. Normally I wouldn't write it, but I will in this case. 1 minus 18, it's going to be a negative answer, and it's like 18 minus 1. So the answer is negative 17, not the final answer. 12 times the number is negative 17. I couldn't even tell you what the exact number was. But I divide by 12 to figure it out. 12 divided by 12 is 1. I'm left with 1x, and I have negative 17 over 12 left on that side. This doesn't reduce. That's a fine final answer. It's correct. They did the right steps at the end as well. Subtract 18 divided by 9, but wrong work leading up to it. So that's all the problems that I'm going to have right here when it comes to solving equations. Hopefully the things that you hear make sense when it comes to logic. I really want to adhere to logic and go to process. I do processes over time. Eventually, this should become very rote, something that you're just, I'm good at it. I'm good at it. I know what I'm doing. And I can justify the steps. Remember addition, property of equality, subtraction, property of equality. It just means you're keeping balance on both sides of an equation. So you keep one side. I can do anything to one side of the equation. I can add a booger to one side of the equation as long as I add a booger to the other side of the equation. I got to keep them balanced. That's the whole idea of, that's called the booger property of equality, okay? So as long as I add 2 to this side, I got to add 2 to the other side. That's what that means. Isolating x by using inverse operations. Double check when you need to. Address errors, see when to combine like terms. I think you're golden with this stuff if you have this practice down. Okay, that was only a half hour of time, not too bad. I wanted it to be faster, but you know what? You're learning. You learn as you go. Hopefully all this stuff makes sense. There's a reason I teach more than just the process, and I hope you like it. All right, so that'll do it for this one. I hope you enjoyed it, and have a good day. Keep learning math, fellas.